What if you can cut your AI agent's latency by 90% and save thousands of dollars on expensive LLM tokens? LLM APIs are one of the most time-consuming parts of an AI workflow, and in this video, you'll learn how to leverage Redis for semantic caching to speed up your AI agent and save cost. It has been a few years since the rise of AI models, and yet a single AI workflow can take few seconds to respond for each request. But of course, latency is not the only problem. Think about the soaring compute cost. A redundant query like "What is AI?" might be processed 1,000 times by the expensive AI APIs, burning through those precious tokens faster than you can say semantic cache. What we're missing is a semantic bridge, a way to stop wasting compute resources on questions we have already answered. To build this bridge, we have to rethink how we search. Instead of relying on exact keyword, we use vectors. Vectors act as a multi-dimensional coordination that represent the meaning of a text. Embedding models act as our translators, turning natural language into mathematical points in a higher dimension space. It's very difficult to imagine a multi-dimensional space, but for the sake of simplicity, you can imagine your exact coordination on the globe represented in two dimensions, latitude and longitude. If you add another dimension for altitude, you get a 3D representation of your exact place on Earth. Now imagine adding another 1,000 dimensions for humidity, temperature, barometric pressure, wind speed, and so on. You get the idea. It's a multi-dimensional space where each dimension represents a different attribute of the text. Once the text is embedded, we can perform a vector search by calculating the mathematical distance between these points. We can find conceptual neighbors, queries that mean the same thing even if they are phrased differently. There are many algorithms to calculate the distance between points in multidimensional space, but the most common ones are Cosine Similarity and Euclidean Distance. Before we go there, let's quickly touch base on the traditional caching. Historically, Redis is known for its key-value caching, which relies on the exact string matching. But in AI workflows, a one-character difference like a missing question mark can completely break a cache hit, which is not ideal for semantic caching. But with vector search, this issue is not relevant anymore. Vector search doesn't care about the exact character match, it's all about the distance between their meaning. We are transitioning from asking, is the string identical, to is the intent or meaning close enough to trigger a cache hit? So how do we actually implement this? We start by Redis. If you have built a RAG application before, you've probably used the vector database to fetch documents and to feed it into LLM. Here, we are flipping the pattern a bit. We are using Redis as the vector store for caching the LLM's output. When a user sends a prompt, the application first generates an embedding for that question and checks Redis. If we find an existing question that is close enough in the meaning, we instantly return the cache response. No LLM call, no API fee, and near zero latency. In the event of having a cache miss, we send the prompt to our LLM interface, get the response, and then save both the question's embedding and response in the Redis for next time use. This is actually a simple middleware setup that can save tons of tokens and reduce your system's latency if it's implemented correctly. This sounds great in theory, but of course, like any other engineering solution, it comes with its own set of trade-offs. For example, we have to tune the similarity threshold to get the best result. If we set the threshold too low, the probability of retrieving relevant responses will decrease. If we set the threshold too high, the system makes repeated calls to LLM, which undermines the whole thing. But that's not all. Let's say that we have the perfect threshold in place, and yet the system is not doing what it's supposed to. There's a fatal flaw in vector search by nature that can lead to incorrect cache hits or responses. Let's consider the following examples, where your system receives two similar questions, like what is 5 times 5, what is 10 times 10, what is weather in Seattle, what is the weather in New York, or what is the current time in Helsinki versus Sydney. If you cache the response for the first prompt, your system will likely return the same response for the second question, because their embedding will be really close to each other. For example, your system will return 25 for the response of 10 times 10, which is way off. One of the most practical and fairly easy approaches to avoid this issue is classifying the prompt into cacheable or non-cacheable categories. A prompt is cacheable if it's deterministic and can be answered by an LLM the same way every time. And respectively, a prompt is non-cacheable if it's non-deterministic or requires real-time information. And you can determine the cacheability of the prompt as an additional step in your agent's workflow. There are other methods for tackling this issue in different ways. For example, restricting the semantic cache to specific domains like refund policies or FAQs, caching intermediate artifacts instead of the final answer, or using confidence band instead of a single threshold. I'm really curious to read more about your approaches in the comments though. In conclusion, semantic caching is a powerful technique that can help you reduce your LLM latency and save cost if you have a solid approach for handling edge cases. Otherwise, it can lead to inaccurate responses with frustrating user experience. If this video was helpful for you, consider subscribing and sharing it with your friends. Until next time, happy optimizing!